So far in this course, we have described the electromagnetic spectrum and the different wavelengths of radiation that comprise it. There are, however, other kinds of radiation that are not based on waves. These are called particulate radiations, and they are made from particles. In today's lecture, we will learn what the difference is between particulate radiation and electromagnetic radiation. We know from previous lectures that electromagnetic radiation is energy transferred in the form of electromagnetic waves. Particulate radiation is not a wave. It is made of particles that originate from the nucleus of atoms. They are created when the nucleus of an atom decays or breaks apart, and we get particles called alpha and beta. Both alpha and beta particles are created by the process of decay in large atoms. Larger atoms, those with atomic numbers of 83 or greater, such as uranium, have a tendency to be unstable and will decay or lose some of their nucleus so as to become smaller and more stable. This is referred to as radioactive decay or radioactivity. Alpha decay loses 2 protons and 2 neutrons from an atom to produce alpha particles. Beta decay loses 1 neutron from an atom and unsurprisingly produces beta particles. Let's look at each of these particles in more detail. Alpha particles consist of 2 protons and 2 neutrons that are emitted from the nucleus. Alpha particles can only travel short distances, a few centimeters, and are not very penetrating. They can be stopped by a few centimeters of air, a piece of paper, or by our clothing. When a large atom decays and emits an alpha particle, its atomic number, the number of protons in an atom, drops by 2. It therefore becomes a new atom with a new atomic number. Large atoms decay until they reach a stable state of an atomic number below 83. One great example is uranium. With an atomic number of 92, uranium is a famous radioactive element. It also has up to 146 neutrons in its nucleus. Uranium undergoes 5 levels of alpha decay to become lead, with an atomic number of 82. So uranium becomes thorium, thorium decays to radium, radium becomes radon gas, which becomes polonium, and then lead. Each of these atoms before lead are therefore alpha emitters and are therefore described as radioactive. The process of alpha decay sometimes leaves the nucleus in an excited state. Gamma rays then remove this excess energy. So with radioactive materials that emit alpha particles, there are gamma rays present too. And as we learned earlier, these gamma rays are electromagnetic radiations. Alpha particles are highly ionizing. They knock electrons from atoms at a rate 1,000 times higher than gamma rays. This is because they are more massive than a photon of electromagnetic radiation. They are therefore the most destructive form of ionizing radiation. Due to the short range of absorption and inability to penetrate the outer layers of skin, alpha particles are not, in general, dangerous to life unless ingested or inhaled. And as they do not travel very far from the atom that produced them, you would have to ingest or inhale the radioactive atom for them to be dangerous to you. Where this does happen in large amounts, death is certain. This was the case for Alexander Litvinenko in 2006. Alexander Litvinenko was a former officer of the Russian Federal Security Service and KGB, who fled from court prosecution in Russia and received political asylum in the United Kingdom. He was surreptitiously given 10 micrograms of polonium-210. That is 200 times the lethal dose. The alpha particles killed him over the course of 23 days. This was a highly unusual event, and the only documented case of its type. Another situation where radioactive material is likely to be inhaled or ingested is after a nuclear power plant explosion, like Chernobyl, or a nuclear bomb explosion like those at Hiroshima or Nagasaki. These nuclear bombs were designed to release huge amounts of energy quickly through nuclear fission, where the nucleus of an element is split into fragments. Heavy elements, such as uranium or plutonium, release energy when split, so-called splitting the atom. The energy released also spreads uranium. The resulting cloud of dust, gas, and energy emerging from a nuclear bomb, when inhaled, injures those not killed by the explosion through ionizing radiation damage. Another more common way to inhale radioactivity is through smoking. As mentioned before, polonium is an alpha emitter and is also suspected of playing a role in lung cancer and bladder cancer related to tobacco smoking. A 1964 paper by Radford and Hunt indicated that for an individual smoking 2 packs of cigarettes a day, the radiation dose to the bronchial epithelium from polonium-210 is at least 7 times the background radiation. Radiation from this source is therefore a significant cause of lung cancer in smokers. A more recent review of polonium in cigarettes reveals that the companies have known about it for years, but prefer not to use the acid wash that removes it because the acid wash reduces the nicotine kick that smokers receive. Beta particles, or beta radiation, is another type of particulate radiation. Like alpha particles, this type of radiation is not in the form of a wave, but a subatomic particle. In this case, it comes from the emission of an electron, sometimes referred to as a positron. Similar to alpha particles, large atoms are needed to produce beta particles. They must also have too many neutrons. As you may know, adding a proton to an atom makes a new element, while adding a neutron makes an isotope, or a heavier version of that atom. One such atom is strontium-90. This is the material most commonly used to produce beta particles. Like large atoms, isotopes will decay to a point where they become stable. They do so through beta decay, a process by which a neutron is converted to a proton, an electron, and an electron antineutrino. Neutrinos are like electrons except they have no electric charge. For each neutrino, there exists a corresponding antiparticle called an antineutrino. Likewise, unstable atomic nuclei with an excess of protons may undergo beta decay as well. This is called positron decay. Here, a proton is converted into a neutron, a positron, and an electron neutrino. Neutrons, as we have heard before, are in the nucleus of an atom. They too can be emitted from isotopes so that the isotope can reach a stable state. Neutrons have zero electric charge and thus do not directly cause ionization. However, neutrons are sometimes referred to as being ionizing because neutron absorption results in gamma ray emission, and gamma rays subsequently ionize. A positron is an anti-electron and has an electric charge of +1, whereas an electron has a charge of -1. They both have the same mass. When a positron collides with an electron, annihilation occurs, which results in the production of 2 or more gamma ray photons. When a positron and an electron meet, they annihilate and give off gamma rays with exactly 511 mega-electron volts of energy. This is a useful process that is used in a type of medical imaging called nuclear medicine, and we will talk about that later in Module 5. So beta particles are essentially electrons, positive or negative, traveling alone. They travel no more than a meter and are stopped by plastic or wood. but they are 100 times more penetrating than alpha particles. Beta particles are used in radiation therapy to treat eye and bone cancers. Here, a strontium-90 source is opened and electrons emerge. The electrons come from the radioactive strontium in a stream. When used in this way, it is sometimes referred to as a beta ray. This can be confusing because it is a beam of particles and definitely not an electromagnetic wave, and nothing like a gamma ray. Because beta particles do not travel very far, if they are used for treatments, they have to be positioned very close to the tumor. Beta particles can penetrate the skin, but not much further than that. So again, to generate a lot of damage, the radioactivity from the isotope generating beta particles would need to be ingested or inhaled. So let's summarize what we have learned about particulate radiation. Alpha particles are made from 2 protons and 2 neutrons, and they are thousands of times bigger than beta particles, and they are the most ionizing particulate radiation and the most dangerous of all radiations if ingested or inhaled. Beta particles are electrons or positrons, and they are given off by isotopes, heavier versions of atoms. Beta particles are used in medical imaging and in some forms of radiation therapy. Beta particles can annihilate and give off gamma rays. So there you have it, radiation in 2 forms, particulate and electromagnetic.